Hello class. This will be a video to show the basics, the entry level of critical path modeling, CPM. This is when we have a series of activities like making the motorcycle helmet and where there's actually some parallel activities which introduce some policy issues and questions that we need to address about which things start first, which things that we can maybe have some slack time with and don't have to start immediately because there are other parts of getting things done, other activities, another path through the activities that define a critical path. So the longest path through a network from start to finish, there may be some parallel items going on. Now that's a little bit different to contrast that with McGraw-Hill practice. McGraw-Hill practice we treat pretty much as a straight linear, nothing happens in parallel. We don't add machines in parallel, like two machines in parallel for doing cutting and sewing and things like that. That's the example where this matters, what we're looking at. And in a complex project, you're going to see a lot of parallel things happening. And this is why you walk into your meetings, walk into your job at all, and you're able to express what's going on at the high level and even at a detailed level with the different activities that take you to delivering to the customer. Okay, so I will let you read a little bit about the origins, about where CPM comes from. It has to do with large projects, especially in the defense industry, coming around in the 1950s, post-World War II timeframe. And we needed a science that helped us predict how long it would take us to get through a project here for bidding reasons. The government was running into some troubles here. The contractors weren't delivering, and there was no organization as to understanding and managing to a schedule with the individual times it took for different activities that it would take. Okay, so the origins came from the defense and aerospace industry with very large projects. Okay, so I'm going to come down here a little bit, and we're going to focus on the bottom of the page down here. And you can do the reading, okay? You can stop, pause, you can do the reading. I'll let you read what's going on here. But we basically have 4 activities. This is a very generic project that we're talking about. And it's the project has to do with collecting some information, making a selection, a criteria standpoint. In other words, definitely qualifying a project before we start. That's the qualifying, selecting a company. And then there's 2 things that happen in parallel. We're going to go and we're going to get the annual report and perform ratio analysis on all the financials. And then we're going to collect some stock price data and perform technical analysis. Okay. In fact, this is actually kind of an interesting problem because the Wall Street Journal basically is interested in fundamentals. This first is going to end up becoming the B activity, and Investor Business Daily, IBD, has to do with doing technical analysis, which has to do not with anything underlying a stock, but just its performance. We're just going to look at stock performance. Doesn't matter whether you're making bagels or you're making satellites. It just depends on what the historic pattern is that you can identify in its stock value. Okay, just has a little bit of an interest. It's kind of an interesting problem. They don't talk about it in here, but that's kind of what we're talking about. All right, so we select a company, we perform 2 different kinds of analysis on it, and then we come together at the end and we review both and we make a decision on, I guess, what we're going to invest in a company. So we designate the first process as A, then we have B and C in parallel, and then D. We finish on D. Now, B and C depend on A. It says so right here. The immediate predecessors, the dependency, is that A has, that's at the beginning. There's nothing, no preceding activity that happens there. B depends on A. C depends on A. Okay, so A is the predecessor to B and C, and then B and C are both predecessors to D. Okay, so let's think about that a little bit, and the fact that A takes 1 week to select a company, and then B takes 2 weeks to do the fundamental analysis on it, and it takes 1 week to do technical analysis on it, and then when we get to all that together, it takes another week. So let's start drawing that. That's what we do here for CPM. We draw the activity network. Okay, so I'm going to flip over to OneNote, and we're going to show how to analyze this. We say we have activity A, draw that in a circle, takes 1 week. And we say we've got activity B, that takes 2 weeks. We have activity C, that takes 1 week. And we finish with D, which takes 1 week. We draw them as a bubble diagram. We kind of show the parallel activities that go on, B and C. And we're going to end up with more complex pathways, more complex networks here. but what you'll find is there's usually a hierarchical representation of what happens anyway. This is a very, very high level drawing, okay, of what goes on. We could break down A into A.1, A.2, A.3 perhaps, all right? And then as you go in and you look at those networks, you'll see more dependencies and more parallelism of the activities going on and whatnot, okay? So we're going to connect these to kind of indicate the connectedness of the network, how it's framed and how it works out. And we're going to introduce a nomenclature here where we'll take A and we're going to go through the network as the early start, early finish network to begin with. And we're going to put these numbers on the top of each of the bubbles, okay? And that's going to be analyzing from front to back, from start to finish, what the longest path through the network is. So at the outset, why we're doing this is we're trying to figure out whether it takes longer ABD than it takes ACD. That's critical path. Critical path equals the longest. Okay. Once we've determined the longest path through here, we wouldn't tell a customer that we're going to do it in any less time. But while we're doing that, we might find things that are off the critical path that are going to have slack time. Okay. So slack time means that it is not tightly coupled throughout the entire path all the way over here. There's actually a wiggle room, if you will. You can start and finish. There's different start times that you could still accomplish reaching D and delivering to the customer. Customer's out here. All right. We're going to make sure that they're really happy. Okay. So we're never going to tell them anything less than what we think it's going to take us by analyzing this. Okay. So the way that we start here is we start in time and we say, okay, and this is by weeks, 1 week, 2 week, 1 week, 1 week. And we really start, early finish. We start with 0 time. We add 1 week. So A1 takes 1 week to get through there, 1 week. We transfer the early finish becomes the early start of any subsequent activities that happen here. So you're going to transfer the fact that B and C both start at week 1. So that's just going to be the same numbers there. Okay, we're drawing these on the top, across the top of all the bubbles in the network. Okay, so we start at week 1, the end of week 1 actually, and 1 plus 2 weeks is going to be 3 weeks. So it takes 3 weeks to get all the way through A1 to B2. All right. If we come down here, you want to work in parallel here, and this starts at week 1, we add 1 week, and it only goes to week 2. Now we're going to see the difference here. CB2 takes longer than C1. So by what I originally said, we're beginning to determine that the possibility and probability is that the longest path is going to be ABD. Okay, so when you determined these early finishes for all of the parallel activities, you look for the largest number and you transfer it over here. So 3 weeks plus 1 week is 4 weeks. So it makes sense. It takes 1 week and 2 weeks and 1 week. Add those together, it ends up at 4 weeks. All right. Now we're going to work through the bottom part of the network. Okay. We've already done is we've determined that ABD is the critical path. Okay. ABD is the critical path coming through here. Now we're going to work backwards through the network. And since it's such a small network, the answer is almost known before it is known before we start out here. We know what the critical path is, and that the only place that there's slack time in this entire network is C. Okay. By logic, because it takes 1 week, we could probably start this at week 2 and finish on 3 and be fine. See, we're finishing right alongside B, which takes two weeks to do. So that's where the policy comes in. Why would we start early or why would we start late? But let's finish the analysis. I'm going to go through the bottom now. Okay, I'm going to go through the bottom numbers we use indicate late start, late finish. We work backwards through the network. Okay, so the way that we start is we take our last aggregating activity here. It aggregates everything else coming in, performs some conversion of the raw material, whatever it might be. Here it has to be information, as a matter of fact. Okay, and we know we're going to finish at week 4. We subtract 1, and we end up with 3 here. You're always going to see the same numbers top and bottom on this. Okay, so now we transfer the late start of D to the late finish of these predecessors. So we put 3 in there. Okay, so 3 minus 2 weeks is 1. Notice that it's the same on the top as it is on the bottom. There's no slack time up here. Okay, there's no give and take. But 3 minus 1 ends up being 2. So we see that if we can either start at week 1 or week 2. That's what we just determined. If we start as late as we can, and as long as we finish on week 3, that's down here, the late finish, then we have a whole week of slack time in here. We can start either at week 1 or week 2. That's what we're after in this, is to understand all the places where we have some slack time after we determine the longest path through here. Okay, so now when we have to finish the model here, we look at the early, coming backwards through the system, we have to look at the late start times. And we want, in a sense, take the worst case and we bring that down. It's going to be the smaller of the numbers. 1 minus 1 is 0. And so you'll see that the first and last events or activities, their early start, early finish should match their late start, late finish. Okay, these numbers will be the same. Okay, so we just performed CPM on this little 4 project or 4 activity project that we have here. It's about as easy as it comes. And the whole idea there is very, very big. We determined that the critical path here was ABD, and the ACD has some slack time in C of 1 week. And we'll talk about the reasons why there's policy around there. It's not black or white, right? Now we have to decide what reasons would we start at 1 week and what reasons would we start at 2 weeks. So now let's take a look at a little bit more complicated, i.e. realistic problem here. Okay, so we have activity A through H. Does that give us 3 and 6 and 8 different activities, immediate predecessors? We have a table here. It shows which activities precede which. And then this will be from a future problem. It's actually problem 4.8, which covers a little bit something different. But here are the times. Just take the M column as the nominal time it takes to get through any one of these activities. All right, so it's a drawing game to begin with. Okay, so there's A. Let's do that again. A says takes 3 weeks. It's days. In this problem, it's days. Okay, so let's do a more realistic problem here. This is problem 4.8 out of Jacobs chapter 4. And we have a list of activities here, A through H, which amounts to 8 processes. We have a table of what the predecessors are in here. It starts to get a little interesting, okay, for us. You don't have to understand that until we start drawing it. And then M just represents the nominal time it takes to get through each of these activities. So we have A is going to be 3 weeks. B has no predecessors either. So this is an interesting problem already. So we have B starts out here. C depends on A and takes 2 weeks by the table. D depends on A and takes 3 weeks. Okay, get a little tight in here. E depends on B, so we have E down here, and E has 4 weeks. F depends on C and D, so we get F here, and F is 4 weeks. G depends on D and E, and G takes 4 weeks. And finally, H depends on F and G. Takes 4 weeks. So we'll draw our connectivity here. As such, that's our network. So we'll start with our early start. Okay, so with A, we're going to start at time 0. Takes us 3 weeks. What we're going to do is bring our 3 over to the early start on C and D. So 3 plus 2 is 5. We end C week 5. 3 plus 3 is 6. We end D at week 6. So you begin to notice things here. We notice that D gets done a week after C2 would if we started C2 as early as possible. Okay, so this is where we bring the longest time from a predecessor over to the early start. See, we can't start F4 at 5th week because we're still working on D3. It depends on D3. So that's why 6 is carried over to the earliest start F can deal with is at week 6. Okay, so 6 and 4 is 10. We have to hang on. We have to take a look at these other pathways through here. So let's come back to B. We'll start at time 0. We get to the finish of B at 2. Nothing too much to think about. We just carry the 2 over to the early start. E starts at week 2. Plus 4 is 6. Okay. And now we can see, we have this issue of parallels coming in, converging, getting aggregated into G. Okay. And they're both at 6, so there's not much to think about there either, because we're going to get through B and E takes as long as it takes to go from A through D, right? It's 3 and 3 is 6 here. 2 and 4 is 6. D and E both finish after 6 weeks. Okay, so we carry the 6. This is the earliest we can start G is at week 6. We add 4, we get to 10. Okay, they're giving us some easy numbers here because we don't have to think too much about this. Both F and G end on week 10, so H can't start until week 10, 10th week. Add 4, that's 14. Okay, so the time through the system is going to be, and I'm sorry I keep saying weeks, but this is going to be 14 days. If I write it down, I keep saying weeks. Okay. All right. Now we don't know what the critical path is here yet. Okay, we have to look at what the critical path might be. And what we see is that there's no real wiggle room from A3 to D3 as compared to B2 to E6 or E4. Both of these have to end after 6 weeks. Okay, so there's no slack time in here. So at the present time, there's equal critical paths. So you can have that. 2 paths can have the same exact amount of time. All right. But what we can see if we go to A3 to C2 is that this can, if we start everything as early as possible, and again, now you might be understanding why they're called early start, early finish. We're thinking in terms of if we start everything as early as possible, then C2, if you're a person working on C2, you're sitting around for a week waiting for D3 and E4 to get finished. Okay. All right. So there's one path in here that is not critical, and that has to do with ACFH. Okay, so say critical path not, we'll draw a little bar over that, is equal to ACFH. Okay, now what it says is that ADFH is equal to ADGH is equal to BEGH. Okay, and that your critical path, there's actually 3 critical paths through here. But let's show that a little more clearly here, and we're going to go through and do the late start, late finish. So now you're getting the idea that the first time we go through this from front to back, that we're looking to find what processes, if we start everything as early as possible, we see that there's slack time here. So slack, the only activity with slack is C2. That's the only activity in here. Everything else, you can see the dates all match up. You have to finish B and E at week 6 to be able to stay on the same timing as A and D to get to G. All right, so slack, the only one is C2. We ended up with 3 critical paths. But let's go through and say, what if we wanted to wait on anything with slack? And oh, by the way, we only have C2 in this example, but you'll have other examples where there's more activities that have slack time in there. Okay, what if we wanted made a policy that says we'll start everything as late as possible? Okay, so that's why we come back through here the other way. 14 minus 4 is 10. Okay, now we can move the late start to the late finish of preceding activities there. 10 minus 4 is 6. 10 minus 4 is 6. Let's do the easy path. There's really not much to think about down here. We'll move the late start from G to the late finish of E, which is 6. and 6 minus 4 is 2. You notice when there's no slack time, keep calling it wiggle room, but if there's no slack time in there, that the early starts and late starts are the same. Okay, you're not going to have any slack time to play around with in there, so we can move the late start to the late finish here. 2 minus 2 is 0. Everything's happy. Just what we would have expected. Okay, so we came through here. Our late start for G and late start for F are both 6. So we can move that over to D. And the way that it works, we can move 6 over to C2. This is going to be interesting. This is the only cell that really makes it interesting here, because 6 minus 2 is 4. Okay, let's hang on there for a sec. Okay, so we move the late start to the late finish of D3. 6 minus 3 is 3. Okay, so when we're moving backwards through the system for the late start, late finish, then we have to look at the critical time here is 3. Okay, what's the earliest of the two? Comparing the 4 and the 3, the earliest is 3. That's how we decide we're going to move this over to the predecessor. 3 minus 3 is 0. The math works out. Okay, and that these first elements or activities and the last element will not have any wiggle room in there, as you can see. Okay, in general. All right, and so C2 is the only cell that had some wiggle room. So the whole concept, let's break back out of that. Let's say it again. I'm just saying it again, is that we could either start at week 3 or week 4. All right, and so if we, in general, if we have a policy to start everything the earliest, we would start it at 3. We'd start at week 3 so that people were sitting around for that last week. Just to give an example of what really happens, people aren't usually generally sitting around waiting for things to happen, but we can start it as early as 3, or we can start it as late as 4, and we can catch up to the other processes that are full bore. There's no wiggle room, there's no slack time in there. Okay, so that's how we determine that there's actually 3 CPs in there, and we list them. Okay, so we gave them the identities of listing the path through there. The only thing that's not critical path is A, C, F, H. So that's an example of a slightly more complicated one, and then we'll work on this. What's coming is this is one of 3 versions of critical path modeling. Okay, the next thing we're going to do is we're going to take a look at what's realistic about this. If you've been running a company long enough and you reproduce or your activities reoccur over and over again, if you're the manager of those, you pretty much well know what the latitude is, how early they might start, how late they might start, how long they might take. Okay, primarily you know from experience how long they'll take. Okay, so what we're going to do is the next step is what I've whited out here so it wasn't distracting, is we're going to say, as a manager, and you're managing, let's say F. Okay, so you have activity F, and that might be putting the visor on the motorcycle helmet, and you know that it takes 4 days to do that. Or in reality, it might be 4 days to do 1,000 helmets or something like that, right? So it's 4 days, but in the real world, we'll say, well, you know what? If everything goes right, it might only take us 1 day, and it might take as long as 14 days if everything goes wrong, okay? And we're going to keep track of some of this data in our company so that we can get more accuracy with this. And what you'll see is this is the optimistic date, and this is the pessimistic date. 1 day to 14. And the nominal, which we actually show here as M, is pretty much on average. Most frequently, we get things done in 4 days. Okay, so we're going to have to talk about probability on this, okay, because as we start entering in this, we're going to have to understand such things as standard deviation, averages, oops, ran off the page here, averages, standard deviations, and take a look, even variances, and we'll get into that in class as the best way to handle that, so variances. There you have it. That's CPM, couple of problems, one an introductory problem, another one which is a little bit more realistic, and then we're going to step into, there's basic CP, there's the 3 time estimates. Okay, so the second time we're going to do this is 3 time estimates. Sometimes it's called PERT, Program Evaluation and Review Technique. Okay, and then number 3 I have to write down here. The third version of this will be schedule crashing. And schedule crashing has to do with real life situation where if somebody pays to speed something up, how fast can we do it? Is it profitable? Okay. So these are the 3 different versions of CPM that we'll do. And the second 2 are very, at least you have to do a basic model that we did here. And then we can add in some variability here, treat it as a random variable. as to how long it will take any one of these single activities to take place. And the third version is schedule crashing, where you could make some money this way. All right. Very good. Hope that's clear, and we can talk about it in class.